Chapter 9, Section 1, Differential Equations. Okay, a differential equation is an equation that has a function and its derivative in the same equation. Now this is about the simplest differential equation that there could be. dy dt, the rate of change of y, is directly proportional to y. So what we want to do is we want to solve for y without having the derivative in it. So how do you undo a derivative? You integrate. So we're going to integrate both sides. Now, it looks like what we just did was divided both sides by y and multiplied both sides by dt. But that's not actually what we did, because dt really isn't a quantity that you can multiply both sides by. What we did was we separated the variables. We want our y's on one side and our t's on the other, and we integrate both sides with respect to those variables. So when I integrate dy over y, I get natural log absolute value of y, naturally. And I integrate k dt, and I get kt plus c. Okay, so like I said, the name of the game here is to get y by itself without the dy dt. So what we're going to do is take both sides to the power of e. So I have just the absolute value of y equals e to the kt plus c. Okay, now what we're going to do is separate the kt and the c. So absolute value of y equals e to the kt times e to the c. Now, you guys know that if you have the same base, that you add exponents. So that's basically what we did, was separated the kt and the c. Now what we're going to do is e to the c is just some random constant. So we're going to call it a. So we're going to say let a equal plus or minus e to the c. Which means now we don't need the absolute value for y, because e to the c will, the a will represent plus or minus the quantity. So that gives us y equals a e to the kt. All right, now what we need to do is see if we can find out something more about a than just some random constant. So we're going to let t equal 0. So if t equals 0, then that means the function y when t equals 0 is going to equal a e to the k times 0. Well, e to the k times 0 is e to the 0, which is 1. So that means y when t equals 0 equals just a. So I can rewrite this then, but I'm going to do one more thing. I'm going to call y at t equals 0 y sub o. That's the initial value of y when t equals 0. So what that gives me is y equals y sub o e to the kt. Now you've seen this before. You don't know that, but you actually have. This is the formula for continuously compounded interest. The amount in your account at any time equals the principal times e to the RT. Remember that a equals pert? That's where it comes from. Think about the amount in your account at any time. That's the general function y. And what's p? It's principal. Well, what's a principal? It's the account balance at t equals 0, at the initial value in your account. and then the k constant becomes the rate of interest. Now we could also use this for population growth. Population at any time is going to be the initial population times e to the RT, where R is the rate of change of population. Now notice that's what we're saying here, is the rate of change of population, or population growth, is going to be directly proportional to the population. What that's saying is a big population is going to grow faster than a smaller population. So population at any time is going to be the initial population times e to the RT, where t is time and r is the rate of growth of the population. And you could also apply this to mass of a radioactive substance. It's going to decay. So it's going to start at some initial value, m sub o, and it's going to decay at some rate, e to the negative RT. So basically, the solution to this differential equation is this equation right here, and there are several applications to this. Okay, so let's go on to the next step, and that is verifying that we got the proper solution to a differential equation. Okay, so what we want to do is show that, okay, we're going to be given the differential equation y prime equals 1/2 times the quantity y squared minus 1. And what we want to do is show that y equals one plus CE to the t over 1 minus CE to the t is a solution. To the differential equation. Okay, so this is basically like if I was in pre-algebra and I have the equation 2x minus 4 equals 6. And I'm saying prove or show that x equals 5 is a solution. Well, what do I do to show that? I plug x equals 5 in there, and I go 2 times 5 minus 4 should equal 6. Well, 10 minus 4 equals 6, and 6 equals 6. So I just showed that x equals 5 is a solution. That's all we're doing here, only it's a little more complicated than back when you were in pre-algebra. Oh, for the days you were in pre-algebra, when life was simple. Okay, so what we're going to do is first, let's find y prime here. Because we're saying y prime equals this. Well, let's show what y prime is. So y prime, I'm going to have to take the derivative here. So that means I'm taking the quotient rule. Oh no, you forgot the quotient rule. Okay, so it's low d high. Now remember, c is a constant here. The derivative of 1 is 0, so the derivative of ce to the t is just ce to the t. So low d high minus high d low. Now this time the derivative of the bottom is going to be negative ce to the t, and square the bottom. And away we go. Okay, let's simplify this mess. So we've got y prime equals, okay, we've got the ce to the t times 1, which is ce to the t, minus c squared e to the 2t. So I just distributed that. Now I'm going to distribute this. Now minus a minus is going to be plus, and we've got ce to the t and plus c squared e to the 2t. So basically, now this whole thing is over 1 minus ce to the t squared. So you can see that we've got a minus c squared e to the 2t and a plus c squared e to the 2t. And then I've got a ce to the t plus ce to the t. So I end up with y prime equals 2 ce to the t over 1 minus ce to the t quantity squared. All right. That's what y prime is with respect to t. Now what we want to do is go the other direction and prove that y prime really does equal 2 ce to the t over 1 minus ce to the t quantity squared using this. Okay, so if we have, let's just go to the next screen then. Y prime equals 1/2 y squared minus 1. When y equals ce to the t plus 1. Yeah, 1 plus ce to the t. Okay. We'll keep it the same. 1 plus ce to the t over 1 minus ce to the t. Well, so let's plug the y in here, and we have y prime equals 1/2 times my y squared. So it's 1 plus ce to the t over 1 minus ce to the t squared minus 1. Okay, see, all I did was I substituted the y into the differential equation. Now, our goal is to show that the y prime in black here is going to equal the y prime in blue that we got from taking the derivative of y. Okay, so we're just going to simplify this giant mess, and this is going to become y prime equals, let's get common denominators here. So it's going to be 1/2 times 1 plus CE to the t squared over one minus CE to the t squared. Now, we have the common denominator under the first term, but the second term has to be minus the 1 plus, or minus 1 minus CE to the t squared. So notice we basically just got the common denominator for what was inside this bracket. So we're adding in that 1 to it. Okay, so now what we're going to do is just put this 2 down here and just say y prime equals, what's on top? Well, 1 plus 2 CE to the t plus c squared e to the 2t. There's my a plus b squared is a squared plus 2ab plus b squared. Now, minus the a squared minus 2ab plus b squared, oops, ce to the 2t, all over 2, oh, that's annoying. Okay, so all over 2 times 1 minus CE to the t squared. Okay, so let's just clean up the top then. So notice I have 1 minus 1 which is no 1s. Then I've got 2CE to the t minus a negative 2CE to the t. So that becomes 4 CE to the t. Now I've got a c squared e to the 2t minus a c squared e to the 2t. That's it. There's nothing else there. So I've got over 2 times 1 minus ce to the t quantity squared. And all I do is cancel that. So that means y prime equals 2 CE to the t over 1 minus CE to the t squared. Now, if you notice, the blue here looks strangely like the blue here. Or the blue here looks like, oops, wrong direction. The blue here looks like the black there. So what we've done is, we've taken the y prime equals 1/2 y squared minus 1, and we plugged in what they're telling us the solution is. And we came out with y prime equals this value. Then we also took y equals this value and we took the derivative of it, so we got y prime. So we basically showed that y prime equals this value whether you plug the solution in here or take the derivative of that. So we've basically shown that this is a solution to the differential equation. Okay, one more thing. Now that we know that is a solution, they're going to give us initial conditions. So what they say is the initial conditions, example 2 on page 591, the initial conditions, y of 0 equals 2. So what I do is I start with y of 0 equals 2, and y equals 1 plus CE, CE to the t over 1 minus CE to the t. So that means y equals, plug in 0 for t. Oh, sorry. Y of 0 equals 2. So that means y is 2 when t is 0. Okay, so this means that 2 equals 1 plus CE to the 0, which is just 1 plus C, over 1 minus C. Now we can solve for C. So if I multiply the 1 minus C to the left, 2 times 1 minus C equals 1 plus C, which means 2 minus 2C equals 1 plus C. Now let's add the 2C over here. So we have 3C equals, and we'll subtract 1 from both sides. So 3C equals 1. That means C equals 1/3. Okay, so if C equals 1/3, then what that tells us is y equals 1 plus 1/3 e to the t over 1 minus 1/3 e to the t. Now, we are not like the godless heathens that leave fractions in fractions. So we're going to simplify this puppy just by multiplying the top and the bottom by 3. So that means y equals 3 plus e to the t over 3 minus e to the t. So this is the specific solution to y prime equals 1/2 y squared minus 1 when y of 0 equals 2. Okay, that's basically what we ended up with, is not just a general solution, but a specific solution. Now, let's take a look on page 590. And what you can see is that y equals 1 plus CE to the t over 1 minus CE to the t is a family of solutions. So for any given t value, we're going to have different c values. So notice on the graph figure 5 shows that entire family of solutions depending on what c is. So what they gave us, though, is one particular value of y for one particular value of t. Now, when I have exactly 1 point there, then I can eliminate the whole family and come down to exactly one solution, and that's this right here. So this is the specific solution to this differential equation at the point t equals 0, y equals 2. But this is the general solution to the differential equation for any values of c and t. So that's it. Have fun with these.